This is lecture 8 on products of groups. The basic idea is how do you go about, in a sense, multiplying groups to create a bigger group. It's a lecture, a pure math lecture on the topic of finite group theory at junior and senior level, and Barnard is the first author of the text that I'm using in the Teach Yourself series, and the title of the book is called Mathematical Groups. If you want details of the book and the course, which I call a lecture set, go to this website for details and click on the tab deGarisMPC. MPC stands for Math, Physics, Computing. Okay, so today's lecture is about the idea of creating a bigger group from two smaller groups. So group 1 and group 2, there's a way of defining a larger group that in a certain sense is the product of those two groups, G1 and G2. Now, quite a few lectures down the road, later than this one, we'll do the opposite. We will, in a sense, divide. We'll take a group and we will extract from it a smaller group. Now, not in the sense of a subset, but in a manner of speaking, dividing. I won't say more than that. But so on the one hand, you can multiply groups in a certain sense, and you can divide groups also. They're called quotient groups or factor groups, but I'm jumping ahead of myself, several lectures. Okay, so before launching into how to define the product of two groups, I need to do a little bit of background. We'll need a tool coming from set theory, and it's called the Cartesian product. Cartesian is the adjective of Descartes, the famous French mathematician and philosopher. A lot of philosophers call him the father of modern philosophy, and he's also the guy who wedded geometry and algebra. If you have a circle can be defined as x squared plus y squared equals the radius squared. That's algebra, but you're talking about a circle, just geometry, this kind of thing. So Descartes, so the Cartesian product is in the context of sets. Okay, so later I'll be talking about a direct product, so a Cartesian product and a direct product. Now it's easy to get the two confused, so remember which is which. So a Cartesian product is in the context of sets. Okay, so you see the term Cartesian product, just think automatically sets, and later I'll give you a distinction between a Cartesian product and a direct product. All right. So what is a Cartesian product? How do you define it? Well, you have two sets, A and B, and you form their product in the following way. Well, firstly, you symbolize it or represent it as AX, just the multiplication sign, B, and you define it as a set of all possible ordered pairs. Remember that from earlier lectures? An ordered pair is that you just have two things, two elements, like A would be an element of the set big A, and little b here would be an element of the set big B. Okay, so and remember, so you just have two elements here, and the order is important, and you have a pair of them, two of them, and since the order is important, you talk about an ordered pair. So this AB is an example, and so this Cartesian product is by definition, perhaps I should put 3 here. By definition, is the set of all possible ordered pairs. So for every possible A belonging to the big set A, and every little b belonging to the big set B. Okay, so let's actually do one. So let's say big A is this set of 3 integers 2, 3, 4, and B is the set of just 2 letters X and Y. So what would A by B be? Well, so A by B would be all possible pairs. Okay, so we could have 2x and 2y, and then we could have 3x and 3y, 3x 3y and 4x and 4y. Okay. Pretty simple calculation. Okay, so that's an example of a Cartesian product. So generalizing a bit, if you had m elements in set A and you had n elements in set B, what would the size of A times B be? Confusing. Okay. So put it this way: if the size of set A is m and the size of set B is n, then the size of A times B, the Cartesian product, would be n by n. And you can just see that from the definition. So you have n possible A's, you have n possible B's, so the total ways, total pairs, ordered pairs you can have will be m times n. Okay, so that's the Cartesian product. All right, let's do another example. Now you've seen this symbol before, big Z suffix 2, and in this text it's a bit confusing. I got a bit annoyed with Barnard actually, but anyway. He changes the use of his notation. Now before, you're probably familiar with this symbol, that Z2 is in effect the set of residue classes. Now it's mod 2, so the old notation, Z2 would be this. The residue class 0, mod 2, and 1, mod 2. If you've forgotten what residue classes were and so forth, go back a couple of lectures. Okay, now he changes the meaning of this symbol. He uses the same symbol, but now it's much simpler. Z2 to him now is just this. It's just the set of two integers, 0, 1. Right? That's all it is. Yeah, quite trivial. All right. So let's find the Cartesian product of two sets, and they're the same. So the Cartesian product of this set with this set, remember it's all possible ordered pairs. So you could have 0 with 0, let's write it out. So you could have 0 with 0, they're just ordered pairs, right? 0 with 0, you could have 1 with 0, no, you could have 0 with 0, 0 with 1, and you could have 1 with 1. Okay, there's your Cartesian product for these two sets, or the same set. And this is now the second way that Barnard in this text uses this symbol. In this context, Cartesian products, he's not talking about residue classes, just a very simple set like this, mod 2. Okay, we've done this. All right. Okay, now let's apply this idea of the Cartesian product, not just to sets, because this is a very general concept, right? But imagine now that these sets are groups. Okay, so instead of talking about A and B, let's talk about G and H. H, or even better, let's say G1 and G2. It's usually H is for subgroups of G. So let's just talk about two arbitrary groups. Let's say they're finite groups for the time being. So G1 times G2. So you take its Cartesian product, and remember it's the set of all ordered pairs. So G1 is just an element of big G1, and little G2 is an element of the group G2, and you have all possible pairs. So if these are finite groups, if the order of G1 is m, and the order of G2 is n, then the order of this product is mn. Okay. Now this product is given a special name because when you have products of groups, you do that a lot in group theory, finite group theory. So the special name it's given is the direct product. Okay. So now we're going to talk about the distinction between a Cartesian product and a direct product. Cartesian product is general, it's for sets. Okay? It's a very general concept. Sets are a more general concept than groups. Groups are very specialized kinds of sets. Okay? Now, when you hear the term direct product, you immediately think groups, okay? Because it's a term used in the context of groups. So in a sense, you can say that a direct product is a special case of a Cartesian product. And what's special about it? Well, you're talking about groups. Your sets are actually groups. So you're taking Cartesian products of groups, and that product is called a direct product. And the answer you get is a group. Well, I'll show that in a minute. So by taking the Cartesian product of two groups, you have to define the binary operation appropriately, and we'll talk about that next. So as long as you do that, then that product, that direct product, is a group. If